Okay, it's a pleasure to talk about Macaulay because whilst he's become a kind of eponym, he's remembered for Cohen-Macaulay rings. He's that Macaulay. There's a computer algebra package named after him. He's actually a rather elusive figure to find out anything about. In particular, pleasure to give the talk here because I'm working on a paper on the work of algebra and algebraic geometry of Macaulay with David Eisenbud. So this is a sort of joint work in progress, and with some difficulties, a sort of picture of Macaulay somewhere in there. It's not a very good picture, but it's the best, almost the best we've been able to come up with. Macaulay was an English mathematician. He was born near Oxford and educated in Bath and at Cambridge. He graduated in 1882 as 8th Wrangler. This is this curious Cambridge terminology you've heard before. It means they published a list of people in order of merit, and he came 8th that year. He then became a school teacher back at his old school for a couple of years, and then went to St. Paul's School in London, where he was the mathematics teacher, or one of the mathematics teachers, for 25 years, teaching just the upper levels of the school, years 15 to 18 in age, and preparing them really for scholarship exams to Oxford and particularly to Cambridge. The syllabus included differential and integral calculus, which it barely does even at St. Paul's these days. St. Paul's is a very elite school. If you don't know the English educational system, St. Paul's is a pretty fierce educational environment. His more distinguished pupils include J.E. Littlewood and G.N. Watson of Whittaker and Watson, who both became Fellows of the Royal Society in due course. Macaulay wrote a school textbook for the school, Geometrical Conics, which Littlewood regarded as very stiff, very hard, dry book. And the emphasis of Macaulay's teaching was very much on self-reliance, and he was that's very much the key to his character, I think. He got involved in the Mathematics Journal for Teachers, the Mathematical Gazette, and that's more or less his trajectory for quite a long period of his life. After graduating from Cambridge in 1891, he took the BSc from the University of London, and in 1895 he published his first paper, which is a paper I'll discuss a bit, and then on the basis of that paper he was awarded the DSc from the University of London, which is at that time the highest qualification you could get from a university in England. Cambridge only began to award PhDs in 1924, for example. So this is who he is. He's in his early 30s when he embarks on research, and he's teaching at St. Paul's School in London. So that up to remind you what he did. It's not, in fact, true, that bit there about it being by exam. I learned only the other day that that's awarded for his paper. The first paper he wrote was inspired by the work of Brill and Noether on algebraic curves and on what's called residuation, which I'm learning from David is, in fact, the key to Macaulay's whole career. And I'll try and explain what that is in a minute. And the paper of Brill and Noether also discusses the Riemann-Roch theorem, which is one of the major theorems of mathematics, really, and certainly of the 19th century. And what we find in looking at the work of Macaulay is that he wasn't very happy with the way that the theorem had been proved. Now, the Riemann-Roch theorem is a counting theorem. You start with a curve, a plane curve, if you're following Brill and Noether, of a particular degree in a particular genus, which is determined by the equation of the curve in this way of thinking about it. So it has something to do with the degree and something to do with the singular points on the curve, if there are any. And the Riemann-Roch theorem counts the number of curves called adjoint curves, which have a couple of properties. One is they have to have a certain degree determined by the degree of the ground curve, and the other is they have to do the right thing by the singular points of the ground curve. If the singular point of the ground curve is a k-fold point, then this adjoint curve has to pass k minus 1 times through that point. And exactly what that means is exactly what was the point of interest in Macaulay's early work. Okay, so this is what he thought was unclear, elided in some way by the work of Brill and Noether was this business of multiplicities of points on curves. Now, this is the question that Brill and Noether had set themselves to investigate. If you're given a couple of plane curves, and I've put them in homogeneous coordinates here, but just think of them as a couple of plane curves, f and g, when does another curve with equation little h equals 0 get itself written in that form? When can you write it like that? If you want to think in terms of ideals, you can think of f and g as the generators of an ideal, and you're asking, does h live in this ideal? And at the risk of repeating myself a little later on, in the old-fashioned language deuterochronica, we don't have the word ideal in this context, we have the word module. These are modular systems, and that, of course, is going to be the title of Macaulay's book, The Cambridge Tract, is the Theory of Modular Systems. Here we have very simple, or the simplest case where the question arises, given two generators of an ideal, when does something else live in that ideal? And Brill and Noether had made a little fuss about this, because they said that the old guys before them had just said, oh, you look at the intersection points, and h lives in an ideal if the curve it describes goes through the intersection points. And this is a simple example to show that that can't be right. The line x equals 0 passes through the intersection of what you have there, which is a parabola and a tangent to it, but it isn't of this particular form. And so they said, okay, it's not enough. The old guys were wrong. You don't look just at the intersection points and see if the curve you're interested in passes through them. You also have to check that it passes through it often enough to the right degree to belong. And if you want to formulate it another way, you know f, you're given f, capital F, you're given capital G. You want to find A and B so that H, your favorite H, belongs. Okay, so you start off with F and G, someone comes up from the audience with H, and the speaker has to find A and B so that this equation is true. So the unknown things are the coefficients of A and B. And it's certainly not enough just to count the coefficients. You get familiar paradoxes. Kramer's paradox is one that tell you that counting the coefficients isn't enough. There's much more work to be done. So this is what was clear to Macaulay. He knew, for example, that there are going to be, or he discovered, I think it's fair to say, there are a number of special cases that present themselves. What do you want to do if one of the curves, let's say f, is a high-order tangent to the curve g at some point? Do you want to study just the case where the curves f and g, where they meet, have the right number of distinct tangents? Is it different if some of their tangents match up and overlap? How do you count these things carefully and correctly? And Macaulay, I have this mental picture of Macaulay as setting to work as a school teacher. These questions about the coefficients are really questions about linear equations. When you write them down and you look at the monomials of that degree and you're trying to solve these equations, these are linear equations. And Macaulay knows perfectly well that you have quite a complicated theory about k equations in n unknowns, right? And that's going to matter. That's what he focuses on. How does this theory work out in this particular case? And he splits it up into various cases, publishes a bunch of papers on this particular topic. And it's not so much that he wants to say that, for example, Brill and Noether were wrong, but there are quite some subtleties involved in establishing that they're right. Subtleties which he's too polite to say so, but from the way he writes and the things he discusses, they're not matched by the predecessors. So he starts off as someone working on what Brill and Noether have done, and he becomes someone who realizes there's quite a lot to do. And in particular, there's one thing which is going to catch him out, I think. At some stage, he becomes very clear that there's a question here, at least. And that's this. The Brill-Noether theorem says, OK, you've got your two curves f and g, and they meet in a certain number of points. And maybe they meet in a complicated way at those points. H belongs to the ideal, defined by f and g, if it does the right thing at those points. That's what the Brill-Noether theorem says. There's no other condition involved. It's purely local. H belongs to this ideal if it satisfies some local conditions which you find by isolating each point and looking there. So you wander around each of the intersection points of F and G. You understand how complicated that can be. You have a full understanding of that. And then you know what conditions to impose on H. It meets these conditions, it belongs to the ideal. It doesn't meet these conditions, it fails. The conditions that H has to satisfy are, in the case of plane curves, entirely local. They're focused and localized exactly on those points. By 1904, when this sequence of papers comes to an end, Macaulay can deal with a number of things. He can deal with singular points with all distinct tangents. He has more in footnotes than in the papers, long footnotes. He has some discussion of when you've got tangents that are overlapping. He can generalize the Riemann-Roch theorem so that instead of having curves of degree n minus 3, when you've got a ground curve of degree n, you've got curves of L, some other degree. And he has a rather geometrical idea. It's a little obscure. It unpacks in modern mathematics probably into three distinct things about what a singular point is. And he's looking for an explanation, or a language, if you like, for talking about singular points, which says that somehow they are distinct points clustered infinitely close together. Right? Now, whether this was something that was completely clear to him, whether he moves away from that kind of language because it isn't so completely clear, I haven't quite decided yet. David and I are discussing this. But this is, for the first 5 papers he writes for these early years, this is his language. It's a geometrical answer to the question. The answer is going to be the Riemann-Roch theorem works provided you unpack the geometry of these points in a particular way. We do know that some people at least read Macaulay's papers. Charlotte Angus Scott had read his papers. Now, she's rather fun, as probably most of you know. She graduated, well, I've said here rather naughtily, 8th Wrangler in Cambridge, but of course she didn't graduate from Cambridge. Not only not 8th, she didn't graduate. It's 1880, okay? But what happened was that women had been admitted to Cambridge some years before, and the results leak out as to where the women were. And when the order of merit is read out, and it's read out from the bottom upwards on some date in early January, okay, at the Senate House in Cambridge, they get to the stage where they've read out the name of the 8th Wrangler, or rather somebody, the Vice Chancellor of Cambridge, whoever it is, says, and the 8th Wrangler is. And the student audience shouted out, Miss Scott, Miss Scott, and threw their hats in the air. Okay, she comes 8th Wrangler, or she doesn't, of course, officially come at all in this particular list. And this caused quite a stir. Lots of letters in the Times. It was allowed after this that women's names could appear officially in the list of Wranglers. Right? They can get a degree from Cambridge after 1945, but they can at least be ranked somehow from this period when Charlotte Scott's cause became a cause célèbre. She, of course, has almost no chances of a job in England. She gets her DSc from London and immediately comes over to this country, to Bryn Mawr, where she has a very distinguished career at Bryn Mawr and in the American Mathematical Society. So she's one of Macaulay's readers, and she has ideas, she's a geometer like him, about how this theory can go. One of the problems with this theory is that you can usually bash out the low-dimensional cases quite explicitly, and then have to write it out in general, and the theory becomes quite elaborate, and she had some ideas for simplifying things that Macaulay said didn't work. But there appears to be a lot of backwards and forwards between these two, and not for the first time, I have to confess that it looks very much as if Macaulay didn't keep letters. So I don't have the letters from or between Macaulay and Scott. I can't find them in Cambridge, I can't find them in London, I can't find them in Bryn Mawr. And this is a little litany which will come by. It helps to shorten the talk, I'm afraid. At the cost of making it less interesting, I don't know exactly what they corresponded about, except when Macaulay puts it in his papers. Just to observe one particular thing, you can think of this way. A double point, right, where a curve crosses itself like that, okay? You recognize, if it does this at the origin, you recognize it because, well, not only does it go through the origin, but it doesn't have any linear terms either. So a curve with a double point at the origin, if you use coordinates centered on the origin, will have quadratic terms, cubic terms, higher order terms, depending on the degree of the thing, but it won't have linear terms. And of course, it won't have a constant term because it passes through the origin. Now, you can think of this as x squared, xy, and y squared, 3 generators of an ideal. So you can ask about an ideal with 3 generators, so not 2. The formalism is a bit different. If you try and do double points and the AF plus BG formalism together, we don't get this curve, which visibly is the 2 coordinate axes. It has a double point at the origin, but it can't be written as so many x squareds and so many y squared. Macaulay knows that 3 generator ideals behave differently from 2 generator ideals, and he has a theory that applies much better for 2 generator ideals than for 3. So he's aware already that there are some complications in what's going on, and I'm just going to pass over those well, a little bit of technical language. When we had the 3 generator ideal, x squared, xy, y squared, the kind of singularity you get is a double point. It's not a 2 generator ideal. He wants to call it that particular kind of point a 2-set point. He understands 1-set points, which you get from 2 generator ideals, and he knows they're okay. And he thanks Scott for saying the 1-set points, then the theorem about the 1-set points, which he calls the 1-set theorem, is the fundamental one from which the whole subject is most naturally developed. And he claims at this stage, partly thanks to contributions from Scott, to have a grasp of that particular thing. Now, you can think of this, if you like, in terms of complete intersections of 2 curves. So he has a theory about 2 curves in the plane with a particular attention to the singular points that can arise. And in 1905, what's the dates? 1905, 1913. Quite clearly what happens is that Macaulay gets hold of Koenig's book, realizes that the high-dimensional theory is much more complicated than the plane curve case, and sets to work to find out what is the... Excuse me. What is the thread that can guide him from the plane curve case that he understands and into the much more complicated higher-dimensional case. And one of the things I want to do is to try and explain to you that this is genuinely a case in which there can be no simple analog of the Brill-Noether theorem. And then I'll hint a little bit as to what bits of the picture Macaulay gets. He gets a lot of the picture, much more than I can put into this talk. So here you have a rational quartic curve in projective 3 space. The homogeneous coordinates of it are s to the 4th, s cubed t. The missing s squared t squared is crucial here, st cubed t to the 4th. So that's the parameterization of the curve. So we've got a quartic curve in space, a rational curve, and we're going to intersect it with a hyperplane. It'll meet it in 4 points. And this curve, the quartic curve, belongs to one and only one quadric, that one, and numerous cubics that pass through it. There's no other second-degree surface through that curve. If the Brill-Noether theorem is true, then any quadric through the 4 points must have an equation of, and the curve must have an equation of this point to get through the 4 points. That's what the Brill-Noether theorem says. It'd be AF plus BG, okay? And this is not going to work out. You can either count the dimensions, right? You've got a 4-dimensional family of quadrics here. But on the other hand, quadrics in projective 3 space form a 9-dimensional family. You want them to pass through 4 points. That leaves you the 5-dimensional thing. Something's missing, okay? So you're not going to get another quadric of that written in that form. It just won't happen. There's not another quadric that goes through the curve. Or you can bash it out exhaustively with coordinates. And if you want to see me do that, you can come up afterwards and ask. The point here is that the Brill-Noether theorem crucially says the condition that some curve belongs to some ideal, or some polynomial defining a curve, belongs to some ideal with given generators is local. You look at where the two generators of the ideal, where those curves meet. And that's all you have to do. Then you have some work, but you only have to do it at those points. What you have here is an example of a situation one dimension up where the local condition isn't enough. It doesn't tell you. You can check the local condition. It is necessary but not sufficient. So something is missing. Something is going on here that wasn't visible, at least, in the case of plane curves. And this gap between what happens in the plane and what happens in higher dimensions is a source of great concern to Macaulay, and I think it's one of the reasons why he shifts over more and more to working in an algebraic fashion and less, if you like, to this kind of geometrical language about clusters. There's still a great concern for understanding what can happen, but the answer isn't going to come up in geometry. After Koenig, almost immediately after Koenig, and more or less independently, we have one of Max Noether's most famous students, which is Lasker, the chess champion. 1905, he publishes a paper in the Mathematische Journalen, which is known to all algebraists, modern commutative algebraists, as the source of the primary ideal theorem. And so this is a long paper. He's in New York. He'd emigrated already. He was the world chess champion. He lived there for 24 years, ran a chess club, defended his title for a long, long time, and in this particular year published, well, not by any means his last, but perhaps his most substantial mathematical paper, in which he introduces, in this slightly cumbersome fashion, the idea of a primary ideal. If you don't know this branch of mathematics, then what you are usually told at this stage is primary ideals are going to be the analog of prime powers. You want to have some kind of analog for this setting of what you have when you decompose a number into a product of primes, and the idea of a power of a prime in elementary number theory translates into this idea of a primary ideal. It's not an exactly close analogy. It's not the case that a primary ideal is somehow power of a prime ideal or vice versa. But what you're going to do is decompose an ideal as an intersection of primary ideals. These primary ideals enable you to count things with multiplicity. You get, it's not quite unique, but if you want to throw in some prime, if you have some primary ideals and their intersection doesn't, you could remove them and not change the intersection. You're allowed to do that. So you wind up expressing an ideal by Lasker's theorem, Theorem 7, as the intersection of a bunch of primary ideals, some of which have varieties that correspond to them, the points in projective space, which are the zeros and some function. And then possibly there's this other ideal here called the irrelevant ideal, which has as its corresponding variety the empty set. This is a novel feature. It's exactly what you didn't see in the plane curve case. You didn't get this guy turning up. And I don't think I want the second one. So it's, this is the old Richard Feynman joke. Feynman used to object to people covering these things up, and apparently said out loud at one point, "What's the matter? Don't you trust us?" Well, I do trust you, but I'm just trying to avert your gaze at this point. So Lasker produces this primary ideal theorem, which is going to be one way of extending the Brill-Noether theorem into this unexpected context where the test for membership for an ideal is not going to be purely local anymore. This irrelevant primary ideal has a corresponding variety, which is the empty set. There's no points on it. You can't check locally at points of the empty set. And Lasker does an awful lot of stuff of this kind, and it sets Macaulay to work. And in 1913, he publishes a very long paper in the Mathematische Journalen, and again, I think I want to skip over some of the technicalities of this. One way of thinking of Macaulay's paper is he's not only caught up with what Lasker is saying, and there aren't so many people who do that. What he's concerned to do is to say, okay, now if you give me an ideal, if you bring me some generators and let them generate an ideal, can I write out the primary decomposition thing? Can I really do it explicitly instead of just having a general theorem about this? And this is not, of course, a trivial matter. It's, in fact, a highly conceptual matter as well as an explicit matter. He has ideas about what it would be for this process to be, in principle, a finite process. You'd have a finite number of things to check, although sometimes they might be rather difficult. And again, I don't want to slog through the ideals here, the methods here. The theory of resolvents, which you see on the slide, is a sophistication of the theory of resultants, which goes back to Sylvester, and is the kind of engine that Macaulay uses to get results. And what he's very concerned about is the way this theory of resolvents, which is quite a sophisticated theory, can somehow nonetheless be a little misleading. And one of the things that he does is to develop a system of concepts which give you explicit numbers. How big is this resolution going to be? When do you know that you can stop? How do you know you've got a primary ideal here? Which gives you the right sorts of numbers, which the theory of resolvents doesn't particularly do. So this is Macaulay's immediately pre-war paper, 1913 paper, in which he, if you like, has moved over to the Kronecker and Koenig camp in the way he's working. It's very explicit in the way that they would have approved of, I think, and it's also an articulation of some of the concepts that you find in Lasker's paper, and it prefigures some of the ideas that come up in the famous Cambridge tract. I wonder if I want to talk to you about those things. I'm not sure I do. There's an interlude at this point, because Macaulay, who has a rather quiet life, at this point has a rather eventful life, or at least I have to go back 1 year. I have to go back to 1911. By this stage, he'd been at St. Paul's for 24 years. He wasn't the senior mathematical master. And when the senior mathematical master left, he thought it was his turn. He'd been teaching the sixth form. He's got a spectacular array of Cambridge scholars produced by him. He's run the school chess club. He's influential in the Mathematical Gazette, all of this kind of thing. And, surely it should be him. And St. Paul's decide that it isn't. Right? Macaulay resigns. He writes in and says, you can't do this to me, and I'm going. And they get embarrassed about this, but he goes all the same. And eventually, they give him a very generous, for those days, a very generous pension. It was £150 a year, which translates into about $15,000 a year in present money. And he goes back to Cambridge. He becomes a fellow of his old college, St. John's, which gives him free meals, and he can manage to live the rest of his life at Cambridge in this fashion. So he gets a sort of, I wouldn't want to say shabby deal, particularly out of St. Paul's, but he'd done them proud. And if you read up in Littlewood's Mathematical Miscellany and see how this was done, it's quite an interesting system. He only taught the sixth form. And the deal was this. You would read the book, and if you were in the lower sixth, the junior group, and you couldn't do something, you were allowed to ask members of the upper sixth, and they should be able to tell you. If they couldn't answer the question, they could then ask Macaulay. And Macaulay has to be able to answer it on the board, there and then on the spot. Okay? This is what I mean when I say Macaulay is very strong on self-reliance. Okay? This is the whole educational system of St. Paul's. Right? You're being crammed through Cambridge entrance. That's really the entrance you want. You're being crammed through the Cambridge entrance. You can talk to the people the year above. If they can't do it, then they get to talk to the teacher, and the teacher has to do it like that. Okay? So he puts certain standards on himself, and it licenses him being able to say that you have to live up to these. So this is Macaulay's immediately pre-war paper, 1913 paper, in which he, if you like, has moved over to the Kronecker and Koenig camp in the way he's working. It's very explicit in the way that they would have approved of, I think, and it's also an articulation of some of the concepts that you find in Lasker's paper, and it prefigures some of the ideas that come up in the famous Cambridge Tract. I wonder if I want to talk to you about those things. I'm not sure I do. There's an interlude at this point, because Macaulay, who has a rather quiet life, at this point has a rather eventful life, or at least I have to go back 1 year. I have to go back to 1911. By this stage, he'd been at St. Paul's for 24 years. He wasn't the senior mathematical master. And when the senior mathematical master left, he thought it was his turn. He'd been teaching the sixth form. He's got a spectacular array of Cambridge scholars produced by him. He's run the school chess club. He's influential in the mathematical gazette, all of this kind of thing. And, surely it should be him. And St. Paul's decide that it isn't. Right? Macaulay resigns. He writes in and says, you can't do this to me, and I'm going. And they get embarrassed about this, but he goes all the same. And eventually, they give him a very generous, for those days, a very generous pension. It was £150 a year, which translates into about $15,000 a year in present money. And he goes back to Cambridge. He becomes a fellow of his old college, St. John's, which gives him free meals, and he can manage to live the rest of his life at Cambridge in this fashion. So he gets a sort of, I wouldn't want to say shabby deal, particularly out of St. Paul's, but he'd done them proud. And if you read up in Littlewood's Mathematical Miscellany and see how this was done, it's quite an interesting system. He only taught the sixth form. And the deal was this. You would read the book, and if you were in the lower sixth, the junior group, and you couldn't do something, you were allowed to ask members of the upper sixth, and they should be able to tell you. If they couldn't answer the question, they could then ask Macaulay. And Macaulay has to be able to answer it on the board, there and then on the spot. Okay? This is what I mean when I say Macaulay is very strong on self-reliance. Okay? This is the whole educational system of St. Paul's, right? You're being crammed through Cambridge entrance. That's really the entrance you want. You're being crammed through the Cambridge entrance. You can talk to the people the year above. If they can't do it, then they get to talk to the teacher, and the teacher has to do it like that. Okay, so he puts certain standards on himself, and it licenses him being able to say that you have to live up to these things yourself. What kinds of things did you have to live up to? Well, the Euler product formula, which Littlewood said was introduced as a joke, rightly enough, and in excellent taste. So that's the kind of thing that you got at St. Paul's. It's pretty impressive. He goes off to Cambridge, and after the war in Cambridge, I'll come back to the mathematics, but I'll finish off on the Cambridge life of Macaulay. He's very slight. He's a prominent member of Baker's tea parties. H.F. Baker is the leading Cambridge geometer of the day, very much in the Italian tradition. And the tea parties, these were Saturday afternoon tea parties. If you were a serious mathematician, either in your final undergraduate year or a graduate, you would be expected to go to these things, unless you were an athlete. Okay, if you were rowing that day, you could turn up late. Otherwise, you were expected to go. And Cambridge had stepped back from the Wrangler system. They'd abolished the Wrangler system some years before, and they'd upped the emphasis of what's called the Smith's Prize. This is a prize awarded for a research paper. You do it after you've done your finals. And the Smith's Prize were and still are very prestigious things. And Baker's tea parties were the source of most 6 out of 8 years of the Smith's Prizes from 27 to 1935 come out of this environment. One of the people who passed through and may have apparently had some of his ideas about Q numbers is Paul Dirac. Okay, there's quite a heavy emphasis here on what is in fact a seminar. It's called the Tea Party. It's the first Cambridge seminar. When Hardy comes back from Oxford to Cambridge, the analysts copy this. This is the first seminar that you have at Cambridge. And Macaulay was a member of this seminar, although, as you'll see, somewhat a distant member of the seminar. Looking at the time and thinking about what I have to say, and knowing how technicalities go over, I think what I want to do is to... I'll just put this one up whilst I'm finding my place. This is what Macaulay based his case for promotion on. 4 senior wranglers amongst his former pupils, 6 Smith's Prize winners, 4 fellows at Trinity College, 1 of his old college, and in successive years at St. Paul's, 2 people who went on to become fellows of the Royal Society. Okay? That apparently isn't good enough to get you the senior position. (1916), not a good year to publish a best-selling book. Cambridge tract of Macaulay on the algebraic theory of modular systems, okay, which is much more than the Annalen paper and much more conceptual than you might have thought. It's a very fascinating mixture of conceptual mathematics and explicit workings with concrete examples. So it starts off with the machinery that he's going to use, the theory of resolvents and the theory of resultants, which he contributes to all of these people. He then goes through the Lasker theory of prime and primary ideals, the Hilbert basis theorem, which he's picked up from Koenig. I don't presently know when he first came across Hilbert's ideas, but David's been persuading me that Hilbert functions are the kind of things that Macaulay has a persistent interest in. It goes as a topic to investigate back before Hilbert. Cayley's word for it was postulation theory, and I think that probably Macaulay starts there, but he catches up certainly with what Hilbert is on about. The Lasker primary decomposition theorem, and then one of the most important of the ideas that he's going to come to. The primary decomposition theorem says if you have an ideal, so think of it as being generated by a perfectly explicit set of generators. You've chosen them, or you've been lumbered with them, your friends have brought these things in. You've got a set of generators for an ideal. Okay, Lasker has told you, and Macaulay's explained how in considerable detail, you can write this as the intersection of a bunch of primary ideals. Now, it may be that some of these primary ideals are contained in the intersection of all the rest. Throw those ones away. Fine. You're left with these others, and what you might suppose, let's take the case where each primary ideal, it's an ideal, so there's a corresponding variety, which is, let us suppose, non-empty. Okay? Now, these ones, these relevant ideals, okay, they give rise to varieties, and if these varieties that they give rise to are not contained in another of higher dimension, you say they're isolated. So the easy case to understand is you really just have one variety, and that's okay. Now you want to say, but suppose we have another variety, and they intersect, and suppose these varieties come with a certain multiplicity. We want to know what's going on. So we have the idea of some varieties as being isolated, and other varieties are embedded. They are defined by things, by ideals, but the varieties themselves are subsets of other varieties. They're embedded. Macaulay isolates the concept of what is called by him an unmixed ideal. And this is one of the concepts introduced by him that goes into the post-war literature, and it's a really very important idea. And he defines it. It's been lurking around as a concept. People knew before that there was something here to be understood. Koenig, for example, had ideas about it, but they're explicitly criticized by Macaulay. He says that the crucial way to define an unmixed ideal is that all the relevant varieties, all the non-empty varieties, whether they are isolated or embedded, have to have the same dimension. Then it's an unmixed thing. And then he starts proving theorems about when do you have an unmixed ideal. And for example, if you start throwing in extra generators and the varieties go down and down in size, they never jump unexpectedly in dimension, for instance. That would be the kind of thing you want. So to go back to the Brill-Noether example, to look a little nervously at David at this point, the Brill-Noether example, okay, you're going to get, you have a curve in space and you have a hyperplane section. Now, they meet in 4 points. Okay? And when you write down the primary decomposition for the quartic curve, okay, you write down as a bunch of primary ideals, and they're all prime. When you take the hyperplane section, okay, something goes wrong, and you get a primary ideal with an corresponding to the empty variety. So you start off with a very nice ideal. You take a very nice curve to which corresponds a certain ideal and a nice resolution of that ideal, a nice primary decomposition. But when you take the hyperplane section, it goes wrong. Okay? And this is where unmixedness comes in. The original ideal corresponding to the quartic curve in space is unmixed. When you take the hyperplane section, it ceases to be unmixed. Okay? And Macaulay has a language for this. He has a concept I don't want to go into, except by means of this example, of perfect. So although the quartic curve is going to give you an unmixed ideal, it's imperfect. When you take the hyperplane section, it ceases to be unmixed. It becomes mixed. You don't have this purely local way of doing Brill-Noether. Something completely unexpected has turned up. And Macaulay now has a way of saying, well, I've got a theory for this. If you've got unmixed ideals and they're perfect, this kind of stuff can't go wrong. Brill-Noether, as a guiding metaphor at least, will continue to work. But if you've got something which is mixed, or if you've got it unmixed but imperfect, then things are going to be completely different from the plane case. So it's one of those moments in mathematics where there's a significant insight into how higher dimensions differ from lower dimensions. Okay, something very unexpected has turned up. I don't think it would be so instructive to say what the theorems are that enable him to recognize an unmixed ideal when one comes into the room. But he does have a bunch of theorems for recognizing when ideals are unmixed. So if you can obtain them, for example, from determinantal varieties of maximal codimension, then they're unmixed. If you have an ideal and the variety has a certain codimension, which is equal to the number of generators of the ideal, then it's unmixed. He has a whole other way of looking at this, which is, instead of talking about the ideals, you can look at the equations that are imposed on the coefficients of any candidate to be a member of that ideal. Right? If you want to be a member of an ideal defined by certain equations, then you write down the object you want to see if it's in. It's some constant term plus something times x plus something times y plus something times z plus so many x squareds and so many xy's. So you write down the whole thing, and you then write down the general member of the ideal, and you start equating coefficients of each monomial. And he then works with the theory of the equations that you get on the coefficients, which determine membership of this ideal. And this turns out, it's a dual way of looking at the thing, but it turns out to be a ring theoretic theory, and it turns out on certain occasions to be an easier theory to deal with. So it's not exactly what he discovers. It's not exactly a kind of straightforward dual, if you like. This is a sophisticated way of doing that. And for instance, you can get ideals in the dual case, which are principal, and that turns out to be very nice, although the corresponding situation before you dualized wasn't so nice. So the theory of modular systems, 1916, okay, is a kind of, well, for a start, it's a book. It therefore gets better distributed. It's one of the things that continental mathematicians can track down along with the Annalen paper, okay? And it has this very rich theory of, polynomial ideals. Macaulay carries on working for quite a long time after this. His papers come out a little more intermittently, as you might expect, because he's pushing 60 by now. But they're very significant papers. A nice one on the Hilbert function, the Hilbert numbers. But I wanted to pass over more or less, because time is running out, to a paper published in 1934 when Macaulay is 72, okay, which is called Modern Algebra and Polynomial Ideas. It's published in the Proceedings of the Cambridge Philosophical Society, and it is the first time in the English language that what we call modern algebra, Van der Waarden style, Kroll style modern algebra, is written up in English. He praises van der Waarden's Moderne Algebra for being the standard work on the theory of ideals. He observes there could be no better example of method than Kroll's proof of Lasker's extension of Noether's fundamental theorem, which has not been published as far as I am aware. And again, I have to say to you that I'd love to know how he knew. I cannot find letters at all. So, you know, was there correspondence between Macaulay and Kroll, which Macaulay assimilated and just binned the way some people do, and they aren't thinking about historians coming along after them? I don't know. Then there's another one, which Grosvenor has used. Again, no reference. So, you know, he knows the work of the Noether School. The Noether School are reading him. M.E. Noether is probably responsible for more entries about Macaulay's work in Fortschritt than anyone else. There's, you know, quite a serious attention to Macaulay's work by her. She cites in the famous 1921 paper, Lasker and Macaulay are particularly singled out as the people who did the theory of polynomial ideals from the standpoint of elimination theory, which is, of course, the way of working that she herself is, if you like, trying to eliminate. But nonetheless, these are the people who did it that way, and people like Ostrowski, Greta Hermann, van der Waarden, and Kroll, all in their different ways, respond to what Macaulay did. Greta Hermann, for instance, is the person who says, well, just how, you know, is this really a finite process? Is his way of spelling out what Lasker did genuinely finite? And she does show that, although with rather absurdly large bounds on what can be done, that it was a finite process. Her paper has been analysed quite carefully by subsequent people, and turns out to be full of lots of little mistakes. I mean, really, chock-a-block full of little mistakes. It makes you rather wonder what her doctor mother did by way of reading theses. But I have been told that Göttingen theses weren't read with enormous care and attention to detail. It certainly can't have been read with attention to detail, otherwise it would have been sent back. But Greta Hermann passed. Kroll often refers to Macaulay in the Idealtheorie book of 1935, particularly for these concepts.
Greta Hermann's absurdly large bounds are actually sharp.
Are they really? Oh, okay, I'm glad to be corrected. I had understood that. I thought they were exponentials and exponentials. And
But that's the way
okay, you're the expert. Thank you for putting me right. I'm happy to be corrected. Unmixedness, which I've tried to indicate the importance of, is one of the concepts from Macaulay that Kroll picks up. Perfectness that I just hinted at, and this idea of working with the theory of the coefficients that you get from ideal membership is termed by Macaulay in a theory called the theory of inverse systems. You might guess that this very explicit way of working wasn't exactly congenial to the Göttingen crowd, and this was Grosvenor's view, that it was artful, obscure, and of little value, although he proceeded immediately to put it to work on a paper of his own. So they did read him. Macaulay dies 2 days short of his 75th birthday, and, of course, merits an obituary. He's by this time a Fellow of the Royal Society. His former pupils and others had signed him in 1928. When he dies in 1938, the obituary is written by Baker, who himself was 72 at this time. It contains a very generous reminiscence by Littlewood, very nice reminiscence, a bibliography by H.F. White, who's the editor of the Proceedings of the Cambridge Philosophical Society, and which entirely omits mention of Macaulay's final paper, published in, well, the Proceedings of the Cambridge Philosophical Society. Okay? It's also, it omits the obituary of Max Noether that Macaulay wrote. It's also a very grudging obituary. There's this suggestion that Macaulay wasn't really up with the literature. And the only sense I have of this is from the little correspondence I have found. There are 4 letters from Macaulay to Baker, essentially correcting Baker. Baker likes to leap over just the kinds of cases that Macaulay liked to zero in on and unpack. Okay? So I think really what's going on is some kind of temperamental lack of affinity between Baker and Macaulay. But it's a very, very odd obituary all the same. And I end, therefore, with some, again, slightly tentative remarks. Not to be too instructive, but this is what a Cohen-Macaulay ring is, and it's a generalization to commutative rings of what Macaulay did for polynomial rings. The generalization was first put forward by Cohen. That's why it's going to be Cohen-Macaulay. We've tried quite hard to find out when this first came up, and our present view is that it's in the literature as Cohen-Macaulay rings in the second volume of Zariski Samuel, 1958. Probably, therefore, in conversation among mathematicians for some time before. But we can't be absolutely certain that when we know this was done. And the other way Macaulay's name is remembered, as you will recall, here's another nearly invisible picture of him, is because of the computer algebra package. And I suppose what I feel, and somewhat I wish to end on, is that the fact that his name is remembered for a concept and for something that does serious computational work is somehow exactly right. That is the mix of things that Macaulay brought to mathematics: conceptual understanding of polynomial ideals and the machinery to answer specific questions about specific ideals. And this development of these two things, pursuing the way in which Brill-Noether theory isn't going to work in higher dimensions, is a remarkable achievement of what I would otherwise regard as, amongst the English at least, a highly isolated and unusual mathematician. Thank you very much.